Hello, students. Let's start today with a hot experiment, literally hot. Imagine a crucible glowing above 380 degrees Celsius filled with molten lead bromide. Sounds like a witch's cauldron, right? But it's pure chemistry magic. In this setup, our electrolyte is molten PBBr and we connect it to a current of about 3 amperes. At the cathode, something exciting happens. Lead ions, that's Pb2 grab two electrons and settle down as silvery lead metal. Meanwhile, at the anode, bromide ions, Br lose electrons and join forces to form reddish brown vapors of bromine. The overall reaction is Pb2 to Br giving lead metal plus bromine gas. One electrode makes shiny metal, the other releases colored vapor. This is redox in action, reduction at the cathode and oxidation at the anode. Now, here's the tricky part. If you take solid lead bromide, nothing happens, no current, no glow, just disappointment. Why? Because ions are stuck, locked in their lattice by electrostatic force. But once you melt it, the ions become free runners on the track, ready to carry charge. At the cathode, you'll see a silvery gray layer of lead forming. At the anode, reddish vapors of bromine rise. And do you know why graphite is chosen as the electrode? Because bromine is reactive, but graphite just shrugs it off, completely unaffected. Quick insight: molten PBBr conducts, solid PBBr does not. That's chemistry's version of heat unlocks the magic. Let's move from molten salts to something more familiar: water. But here's the catch: pure water is a terrible conductor, almost an introvert. To make it social, we add a little dilute sulfuric acid. Now, water splits into hydrogen ions and hydroxide ions, while the acid provides extra ions to speed things up. At the cathode, the reaction is simple. Two H plus ions combine with two electrons to form hydrogen gas. And not just a little, it collects as two volumes. At the anode, hydroxide ions lose electrons to form oxygen gas, which appears in half the volume compared to hydrogen. So the ratio: 2 parts hydrogen to 1 part oxygen. Perfect for making small-scale rocket fuel. This experiment is a favorite because it proves that water really is H2O. At the cathode, hydrogen ions win the race against sodium or other ions. They are faster and get discharged easily. That's why you see bubbles of hydrogen gas. At the anode, hydroxide ions discharge in preference to sulfate ions, producing oxygen gas. Now comes the fun test. Bring a burning splint near hydrogen, it makes a small pop sound. Bring a glowing splint near oxygen, it relights. So, the overall reaction is two molecules of H2O give two molecules of H2 plus one molecule of O2. And yes, you just created the same gases that are used in space shuttles. Now, let's bring in the star of industry, copper sulfate solution. Place copper electrodes in it and watch what happens. At the cathode, copper ions, Cu2 grab two electrons and deposit as reddish brown copper metal. At the anode, copper atoms quietly dissolve into the solution as Cu2 ions. The balance is so perfect that the blue color of the solution doesn't even change. What you lose at the anode, you gain at the cathode. This principle is exactly what's used in electroplating, to coat metals, and in refining to get pure copper. So, electrolysis here is not just science, it's business. But what if we swap the electrodes for platinum or graphite? Aha, now the story changes. At the cathode, Cu2 ions still reduce to copper metal and deposit. But at the anode, platinum doesn't dissolve. Instead, hydroxide ions discharge, giving oxygen gas. The solution loses copper ions steadily, so its lovely blue color fades away. Isn't it fascinating? Just changing the electrode type flips the products. With active copper electrodes, the color stays. With inert electrodes, oxygen evolves and the blue vanishes. This shows how electrode material isn't a passive choice, it actively changes outcomes. Let's wrap this up. From molten lead bromide, we learned how Pb metal forms at the cathode and Br2 gas escapes at the anode. From acidified water, we saw hydrogen and oxygen appear in the Ne2:1 ratio. From copper sulfate with copper electrodes, we discovered the secret of electroplating, balanced copper transfer. And with inert electrodes, we saw oxygen liberation and the fading of the blue solution. So, what's the big takeaway? The electrolyte and the electrodes decide everything: who gets discharged, what forms, and how useful the process becomes. Electrolysis isn't just a lab stunt, it's at the heart of refining metals, making fuels, and even powering tomorrow's technologies. To sum up, chemistry once again proves itself as both an art and an engineer, deciding whether we get shiny deposits, colorful vapors, or useful gases. I hope this session gave you a fresh perspective on how controlled electricity can split matter into useful parts. Until next time, keep experimenting, keep questioning, and remember, chemistry is the magic show where electrons are the true magicians.